So, yes, I'm presenting OpenMP-RT, native Pragma support for real-time tasks and synchronization with LLVM under Linux. So the reasoning is that this is for real-time systems that are under strict timing constraints and during development, more specifically, predictability of timing, or constraints on the predictability of timing. With them being increasingly prevalent and an increasing desire to leverage multi-core systems for use in real-time systems, there's a use case for real-time multi-core programming framework. So since they're subject to timing constraints at runtime and predictability of execution time, parallel systems obviously leverage multi-core architectures for performance improvements. There's difficulties in combining the two due to many existing frameworks for parallel issuing certain real-time guarantees. One example just is in unmodified OpenMP, the priority, or assigning a priority to a task in OpenMP is actually just a suggestion according to the specification, which works fine for OpenMP, but not for real-time systems. So I can skip this slide. This is from something else. So the objective here was to develop a framework for creating parallel real-time tasks, to reduce the code complexity in creating real-time tasks. There's a comparison slide for that. And to support both coarse-grained and fine-grained parallelism. In this case, that means coarse-grained, i.e. tasks themselves executing in parallel on separate threads, as well as fine-grained being individual tasks being composed of multiple threads operating in parallel. And then implement synchronization methods for inter-task communication, sharing across these parallel tasks. So for this, we have the RT task concept, a Pragma that we've inserted into modified OpenMP runtime to enclose a single periodic real-time task. We leverage the kernel scheduler for actually scheduling this task. So in our current implementation, it's restricted to Linux because Linux, with the PreEmpt-RT patch, does already support EDF, earliest deadline first, and static priority scheduling for threads. And then we incorporate lock-free synchronization via two separate methods. Specifically, though, we have a per-priority thread pool and lock-free synchronization to allow for multiple scheduling paradigms to coexist separately. In this case, we can have both EDF tasks scheduled under EDF, earliest deadline first, and static priority tasks existing separately, as well as, of course, lower priority real-time processes. We do cover that in the synchronization, but actually scheduling them is outside the scope because that's a studied problem. So the RT task construct with an example implementation, or an example invocation of it there, is associated with a single dedicated periodic real-time thread. It may pull from its given priority or from the given thread pool for the EDF priority band if it expresses fine-grained parallelism. But it is the Pragma encloses the code for a single RT task. Notably, it's associated with just a name rather than any of the information required for the expression of a real-time task. That's abstracted to a configuration file that I'll go into in a little bit. This, as you can note, incorporates fine-grained parallelism as well by enclosing an OpenMP parallel section containing two threads, and then using the OpenMP task Pragma internally. To express the code reduction when invoking an RT task. So this is an example, or the code example on the left is what is the sequence of calls used to express a EDF task in Linux right now. Then using RT task, this is what that ends up looking like because everything on the left is abstracted to the modified OpenMP runtime and to the code generated by the LLVM compiler. So to express how the thread pools work, RT tasks at a given level of priority pull from a shared pool of threads. The size of this pool of threads is determined at compile time. So thread pooling does already exist in OpenMP. Let me see. Yes. So to express for contention over an example of an issue that can come up is in contention over threads pulled from the shared pool with shared processors. So in this case, assuming that both the red and blue tasks are on the same priority level, we show here that when assuming they both express fine-grained parallelism internally and share 2 of the 4 available cores, in this case, it's non-deterministic which task will enter its parallel section first. So we end up with this contention and then unpredictable runtime. Red, in this case, effectively is single-threaded, and that violates earlier what we want with periodic runtime, or with, not periodic, sorry, predictable execution time. So to combat that, you'll note in the configuration file does establish the configuration file is passed in with the program in addition to the source code. And this is used to tie the name of given RT tasks to the actual real-time properties, period, execution time, phase, and depending on, and the actual scheduling paradigm that it will be under, either EDF, in which case there is no priority passed in, or static priority, in which case there is a priority listed, as well as defining both the cores that are available to to each given thread, or to each given task, each given RT task, and thus the threads that it pulls from the pool, what cores they can be assigned to, as well as defining the shared variables for task synchronization, sharing data between RT tasks. And so the reason for specifying the cores is specifically to avoid the problem we see here. Since if we go back in this slide, we can show that by partitioning the cores separately, we avoid that contention here, and thus our worst case time for red or blue, because this could have gone the other way, is significantly improved. So, so this is the project structure with both the application code and the configuration being passed into the LLVM compiler, containing the modified OpenMP runtime to produce a binary executable with OpenMP-RT. So for the intertask communication, there are 2 methods for OpenMP-RT, a retry-based method and a double buffer-based method. They have some advantages and disadvantages that I'll go into. There was a lock-based deadlock-free method using a total ordering of locks created purely to compare with the 2 lock-free ones. That also shows up in the data. So for synchronization using the retry method, there's read and write pragmas that can be invoked from within an RT task or outside an RT task for communication across the real-time barrier. We use these, or the way these work is by updating, there are 2 timestamp registers associated with each dependency variable. We don't really specify there aren't limitations on the type or size of the dependency variable. That's just passed into the Pragma. But with 2 timestamp registers, on a write attempt, move out of the way here. On a write attempt, the top timestamp is overwritten, and then data is written. Then at the end of, or once the write is complete, the timestamp value from the top will be copied to the bottom. Or rather, the red timestamp value will be written to the bottom. So both timestamps should, on a successful write, have the same value. With a read attempt, we can check the top timestamp, read it, and then check the bottom timestamp. And if the bottom timestamp is different from the top, this indicates the data was invalid. Either a write attempt went through during or either the write attempt went through during the read and thus invalidated the data that was read, so read has to go back and attempt the read again. This retry on the read will continue until either the maximum number of tries is exceeded, in which case the read fails and it's up to the programmer inside their RT task or inside their code to figure out what they want to do from there, or until you get a success. The maximum number of retries is configurable. So for the double buffer synchronization, this has greater space complexity, requiring 2 buffers instead of just 1 to write to. And then a single pointer field. This is per dependency. This, incidentally, is why dependencies do have to be listed in the configuration file so that this can be set up at compile time. So 2 buffers with a single pointer field. At any given time, one of the 2 buffers is considered readable, the other writable. So on a write, the writable buffer is written to, and then the pointer value is swapped. Then a read just simply checks the pointer value, reads, and then we'll simply check the pointer value and read. This prevents the reads from failing, but does have increased space complexity in memory. So for the experimental analysis, we targeted specifically the C language. C++ support should be in there, but our test code was all in C, so for now we say C language support. With experiments conducted using synthetic applications generated using or containing multiple RT tasks expressing both, always expressing coarse-grained parallelism, but also in some cases expressing fine-grained as well. These synthetic applications were assembled using using applications taken from the BOTS, Barcelona OpenMP task set, and the EPCC benchmarks as component RT tasks. So each of the small ones taken from those benchmarks would be used as a single RT task, and then a synthetic application would be composed of just multiple RT tasks smushed together. The table here just shows the worst case execution times for both sequential or 2-core fine-grained parallelism versions of each of the benchmark tasks. So each one of these would have been 1 RT task. You can look at the actual benchmarks to see what each of these do, but some of them, like the FFT, is fairly obviously the fast Fourier transform. N queens computes the number of queens on a chessboard. And so 100 randomly generated test applications were used. For utilization stress tests, see how high we could crank the utilization of a OpenMP task set before, or OpenMP-RT task set before we had failures and deadline misses. We got up to 0.93 or utilization per core. So utilization in this case was uniform across cores for our 4-core system. So this is a per core utilization of 0.93. And we were able to get that high without any deadline misses. At anything below 95% utilization on per core. So for comparing the intertask synchronization methods, in this case, an application with 4 RT tasks on 2 cores in producer-consumer pairs. And in this case, transferring 64 by 64, or 64 byte by 64 byte matrices between pairs. So there are 3 cases. This is looking at both across or within real-time applications and then across the real-time barrier in both directions. So, and then recording the average response time for consumer tasks, since producer tasks are less limited on that one. We did record the producer tasks, but they were similar in, or the data was of the same shape. It was basically the same, so it was cut from this presentation for space reasons. And so that could actually be bigger on the slide. Significantly lower response times were observed using the lock-free methods than the lock-based methods. Specifically, the double buffer had the best response times. And this, I'll note, this is utilization. That's total utilization, not per core utilization, which is why it starts at 1.2. And so the improvements aren't really visible until utilization gets fairly high, which for obvious reasons. When utilization is fairly low, not a lot of the response time is limited by contention on inter-task synchronization. For looking specifically now at the retry-based method, because it has the non-deterministic reads that may or may not fail. So in this case, we have a 2 RT task system on 2 separate cores, just communicating across cores, recording the number of failed read attempts versus the ratio of the producer period versus the consumer period. In this case, just representing, say, a sensor with a high refresh rate, sending data to some internal process in a machine. And in all 3 cases, for the whether or not this data crosses the real-time barrier, it's fairly similar in behavior. So the frequency of rereads does increase as we expect with the, okay. This is basically my last slide anyway, so that works.
Can go to the next slide. Okay, thanks. Okay, questions? We have no time limit, right? Because I have a lot.
Oh, I see. What did you do for the lock-free programming? How did you implement it, and why the performance is like this?
So with preventing deadlocks in the lock-based one that we compared to, or just an explanation of the lock-free communication method?
Yeah.
Yeah. So the lock-based one that was deadlock-free was just using a total ordering of locks based on the order in which dependencies were accessed within the program. That was just for comparison. That used the lock API that's just provided in Linux. For the lock-free ones, with the 2 of them, they don't, or those were implemented using atomic instructions where necessary, such as for updating the timestamps. In fact, yeah, such as for updating the timestamps or updating the pointer value here. And then,
how do you know they are atomic? I
ah,
mean, on what machine are you running this? How do you know they are atomic?
the atomic instructions, just using the, what is it? I'll have to go back and look at I'll have to go back and look in my code, but using the atomic instructions. This was running on an x86 machine, so I'm not actually certain how the atomic instructions at the level that I'm writing this are implemented on the hardware, but I do know that atomic compare and swap is provided to C programming on Linux running on x86 machines.
Further questions? If not, then I have one. Actually, many. So I ask one of them. You mentioned that you use Linux, right? But OpenMP can also be executed on RTEMs as a real-time operating systems as well.
Yes.
So which specific operating system support you need in your approach from Linux?
The reason for that was that our modification to the OpenMP runtime leveraged specific calls used by the Linux scheduler. This could be done on other operating systems that provide real-time scheduling at the operating system scheduler, but A, that's an implementation problem. That's something that we need to extend our implementation for, and B, it does need to be provided in the operating system.
But can you roll back to
Yes.
what you said earlier about the scheduler of Linux? It's actually this one only, right?
Yeah.
So of course, every operating system has its own schedule and specifications of test control block, but you can actually adapt to that, right? So maybe you can have a look of other operating systems that currently already support OpenMP. So it could be a general approach that you have proposed, but
Yeah.
okay. Any more questions? If not, then next time speaker.